Hello, I'm the multicoloured Mr. Daycock, and as I promised in the last video, I'm going to show you why that particular form is justified as our solution to second order differential equations where the auxiliary equation has equal roots. Okay, so let's go back to where we were before we knew that form. Let's just consider this. Now we justified the auxiliary equation of alpha squared minus 4 alpha plus 4 equal to 0 will solve this equation, will give us the right roots. But we also know that this is just going to give us roots of alpha equal to 2 twice. And so it was tempting to go, well, y is equal to a e to the 2x plus b e to the 2x, but that can just collapse to y equals c e to the 2x, and we literally only have one arbitrary constant. But we know, because it's a second order equation, that it must have two arbitrary constants. So, to account for that, what we do is we say, well, what if there's a multiple on there? What if it wasn't y equals a e to the x, or e to the 2x in this case? What if there was an f of x here? What if there was a function being multiplied on the front and we wanted to know what that function is? Now this might seem like I'm being very specific and I'm not justifying why it has to be multiplication, but in fact the whole thing is still just an arbitrary function. Let's say it turned out that y was meant to be equal to the natural log of 2x, or something like that. Well, that just means that my f of x, to make that work, would have to be the natural log of 2x over e to the 2x. So this is still entirely general. It's just as good as writing y equals just some f of x in general and just not knowing what it is, except that by writing it as this product, it turns out to gives us a really easy way of identifying what this f of x must be. It's still really general, it still completely encompasses all the possibilities, all the infinite possibilities of what this function could be, of what our solution should actually be, but it does it in such a way that it allows it to work out really nicely. Okay, so now with that said, let's have a look at what dy by dx must be, because we've got this, we're saying, hey, this might be our form. So what happens when we plug it in? Well, dy by dx is going to be the derivative of one times the other plus the derivative of the other times the one. It's our product rule. We took two things multiplied together. We're going to use our product rule. So we get f dash of x e to the 2x. And then other way around, just f of x plus multiplied by 2e to the 2x. Or I can write that with the 2 in front, plus 2 lots of e to the 2x. And then I can find out d2y by dx squared by just differentiating again. And we're going to have two different parts to it this time. So I want to differentiate this function first, this part of it first, and I'm going to get, well, the derivative of f dash is f double dash of x, still multiplied by e to the 2x. And then the derivative of e to the 2x is going to be 2e to the 2x, and the f dash doesn't get differentiated again. So we're good, it's just like that. And that's just the blue part. Now let's look at this as the green part. Well, we're going to have to also differentiate that and see what we get. So we're going to be adding on, for the green part, well, if I differentiate the f dash, I'm going to have two lots of f dash of x e to the 2x, because I'm just differentiating the f. And then for the product rule, differentiate the other way around. Now e to the 2x, I'm going to get another 2 down, so it's going to be 4. And then its f of x hasn't been differentiated, multiplied by e to the 2x. And that's my green part. Okay, and so now we have these three different parts to it. We've got the black one up here, we've got this green part here, and we've got the magenta part here. And these are the three different parts that we need to plug in to try and find a solution. We know y is this, dy by dx and 2y by dx squared. We have all of those. And then let's go back to remember what the original equation was. It was d2y by, in fact, let's use the colours already here. We've got d2y by dx squared minus 4 lots of dy by dx plus 4y equals 0. Now we can just plug all these in. So in magenta we have f double dash of x e to the 2x. And now notice we've got 2 lots of plus 2 f dash of x e to the 2x. So it's going to be plus 4 f dash of x e to the 2x. And then we've still got plus 4 f of x e to the 2x. And that's everything for d2y by dx squared. Now we're going to subtract 4 lots of dy by dx, and dy by dx is this, so we're going to plug that in. We get f dash of x e to the 2x plus 2 f of x e to the 2x. And then lastly we have to add on 4 lots of y, which is 4 lots of y was just defined at the start to be f of x e to the 2x equals to 0. Okay, and now we can simplify. So we've got f double dash of x e to the 2x. That's of course from the first term. And then we also have plus 4f, there are no more f double dashes, that's the only f double dash. So we've got 4f dash of x e to the 2x, that's from our first term still. But we do also have minus 4 f dash of x e to the 2x from our green term. And now that is all of those. And now we also have 4 f of x e to the 2x from our first term. We have a minus 8 f of x e to the 2x from our second term. And we have a plus 4 f of x e to the 2x from the last term. And that all must equal 0. But let's actually pay attention to what's going on here. This and this are going to cancel because they are exactly the same term, but one's positive and negative. And same here, all of these are going to cancel because 4 and 4 make 8, and then we're subtracting 8, so they all cancel. And we are left with just f double dash of x e to the 2x equals 0. And this is the key equation that we've derived that's going to let us find out what that extra bit is, what that f of x must be. Now, e to the 2x cannot equal 0. There's no chance of that, so we can just divide through by it, and we get f double dash of x must equal 0. That is the only possible way that this equation equals 0. And this is just a very simple antiderivative situation. It's technically a differential equation, but it's just antiderivative. If I integrate both sides, well, on the right-hand side, I just get an arbitrary constant, because if I integrate 0, I just get an arbitrary constant. On the left-hand side, I remove one of the derivatives, so I get f dash of x equals just b, just some constant. And then I integrate both sides again. Well, if I integrate a constant, I just get a constant multiplied by x. So I'm going to get bx plus another arbitrary constant, which we'll call a. And if I integrate the left-hand side, I just get f of x. So my f of x has to be bx plus a, or my f of x is going to be a plus bx. And now if we go back to the start, if we remember our original starting point, we said we were trying this here as our solution. We're trying y equal to f of x multiplied by e to the 2x. But we've just worked out what f of x is, and so our general solution must be y equal to a plus bx multiplied by e to the 2x. And that is why, that's the algebraic justification of why we end up with this x here. Okay, thanks for watching, and I'll see you in the next video where we go on to a slightly more complicated, that's a slightly more complex result you can get from auxiliary equations. Thank you very much for watching, and I'll see you in the next video.